Okay, now that we have chapter 7 done, we're starting chapter 8. And so we're going to be doing lots of examples with circular motion. Some of it's kind of related to what's in the textbook. I have 3 different examples that I want to talk about related to circular motion, and it's all kind of related to cars going down, up and down different hills or in different circles. So just as a very quick review, for particles moving in a circle, we use this so-called RTZ coordinate system. This is in the general playlist, but just really quickly, what's the RTZ coordinate system? We have, our standard XY axis, and we have a particle that's moving with the radius r, of course, moving in a circle with velocity v. We established in chapter, it's supposed to be a y, we established in chapter 4 that if it's moving in a circle, it has to be accelerating towards the center. It's got a so-called centripetal acceleration. And so what we do, the free body diagram that we draw, because the forces always are changing, we draw a coordinate system that is, in a sense, moving along with the particle. So we have an r-axis points towards the center, and a t-axis that points in the direction of motion, and then a z-axis that points perpendicular to that. So we got 3 different axes. Usually we'll use the RZ axis. That'll be the one that's more common. Maybe RT in a couple of later examples. Yeah, especially with vertical circles. But yeah, this is the setup. And so when we have this coordinate system set up in this way, then for uniform circular motion, then the velocity is strictly in the t direction. It's omega times r, or if you like, 2 pi r over t. That's what angular velocity is, right? Lowercase omega, Greek letter omega, has a symbol for angular velocity for particles that are moving in a circle. Later it'll have the term angular frequency for things that oscillate, like springs and electric currents and all that stuff. So velocity is stuck in the t direction. Acceleration is now only in the r direction. V squared over r or omega squared r. Either one is fine. And so the dynamics then show us that for a particle moving in uniform circular motion, that F net has to be in the r direction as well. So that's something that we can kind of ride right next to the acceleration. Just say right here, F net in the r direction is equal to ma, which is equal to mv squared over r, the one we'll use usually, or r, also m omega squared r. And which one do you use for which problem will depend on the context. Typically, if we are dealing with a particle like a car or something that's turning a corner, it's going to be more helpful to use velocity. If we're dealing with like something that's spinning very quickly, then angular velocity is more useful. Okay. So let's do some examples of turning a corner and then. So this example is in the textbook, and it's even mentioned briefly in the chapter 8 videos, but it's worth going through ourselves. So turning the. Right, the typical setup for this example is that you got a car that is making, say, a left turn, and taking that left turn at a constant speed, right? So the question, how do you analyze this example? Well, you have several things to consider. First, how big is the radius? Because this is the part that's relatively uniform in circular motion. So we can estimate what the radius of this is. If it's a typical 2-lane sort of set up, 5 meters would be kind of a lower estimate. Maybe 10 meters might be a little bit better. Let's say 10 meters. So we'll estimate that the radius of this curve is 10 meters. So the question is, how quickly can we take this turn without sliding? And how do you draw the free body diagram? Well, the RT axis isn't that useful in this simple uniform motion problem. So what we do is we'll draw kind of the cart, side or back view of the cart. I know this is not a pretty picture, but this is the back view of the cart. So there's the license plate, and it's moving. And so let's use this RZ plane of the RTZ coordinate system. It's supposed to be an R, and typically the R axis will be on your left. So that is the direction of positivity, okay? So what's interesting about this example is that if we're moving in the circle, okay, Newton's laws say that we have to be accelerating towards that corner. So we have an acceleration towards the corner, which means as we're following this car turning, F net has to be in the R direction. I can write better than that. Okay, so F net is in the R direction. What are all the forces now? We have, our typical normals and our gravities. Mg points down, vertically downward as always. Well, not always. And then N points up. And then, so we have to figure out, so if the normal force points up and gravity points down, what is the force that's producing this circular centripetal acceleration? And you have to ask yourself, well, there's got to be something pushing or pulling the car towards this center as it's moving. And the only other option is friction. And so we say that the static friction force, it's a static friction force. So F sub S. It's static friction force that's providing this centripetal acceleration to keep us moving in a circle. And static friction comes up a lot when we're talking about tires on the road, and especially with rolling motion. We're not talking about a force in the direction of motion or a direction against motion of travel. What we're talking about is a force that is pushing perpendicular to the direction of motion. So like if I draw, the book has this sort of drawing like I'm going to draw here, but so basically if this is like your tire, right, and it's moving, the static friction force is applied like that, right? It's on obviously at this point of contact, this isn't a great drawing, but obviously it's at that point of contact pushing it towards the center of the circle, even though it's moving that way. That's a static friction force. And so, but as you know, static friction has its limits. A surface can only apply so large of a static friction force before it's not big enough to support it and the thing will start to slip. The mental picture that I'd like you to have for static friction would be, let's say you're trying to move a table, right? And the table's on carpet, okay? So let's say you try to push it with your index finger, okay? So you stick out your index finger and you just try to push it with your index finger stuck out. So that's like a tiny applied force matched by a tiny static friction force. So the carpet really has no problem applying the force necessary to counter your push with your finger. And then what happens if you just try to do it with your hand? The push increases and the surface can still respond. I mean, if it's not moving. Only when you really like, plant your feet, push back on your feet, and push forward on the car or on the table, do you have a large enough push so that it'll start to slip. Once it starts to move, then the static friction force is at its max. So F sub S max, that's what we call it. And that force is equal to what we call the coefficient of static friction. We've been working with kinetic friction a lot. Yeah, this force is equal to the coefficient of static friction times the normal force, again, in this model of friction. So we'll keep that with us in the next examples. Okay, but we can sum these forces here. Now we'll sum them in the R direction and the Z direction. The Z directions are standard N minus mg equals 0. And in our R direction now, even though these point to the left in our diagram, the static friction force is still positive. And it either equals MA, MV squared over R, or M omega squared R, which for us, it's usually more helpful to do that. So that's how you would sum the forces. Typically in the problems like this, you're asked for like maximum speed. So how would you find the maximum speed? You have to look at the equation here. At maximum speed would be when the friction force is the largest. If you take it any faster than that maximum speed, you're going to slip. Right? Your tires will start to squeal. You might drift a little bit. There won't be enough static friction. So we just change the R equation to F sub S max which equals coefficient of static friction between tires and road times normal force. That equals mv max squared over the radius. Right. Normal force is equal to mg by the z equation. And so we've got mu sub s mg equals mv squared over r. Notice how the masses cancel, right? And so just multiplying by r and square rooting, we get an expression for V max, which equals square root of coefficient of static friction times radius times g. The coefficient is 1. Radius we assumed was 10 meters. That's not that bad of an assumption. And then g is 9.8. So this is like square root of 98, which is very nearly, 10 meters per second. Which, if you multiply by 2 1/4, is about 23 miles per hour. So that seems reasonable, actually. It seems reasonable that if you were to take a left turn at 23 miles an hour, that tires might start to screech. Would you drift into the other lane? Maybe, maybe not. The tires that they design, they're meant to be with the treads as thick as they are. Like treads start at like 9 or so millimeters. There's a lot of grip on the road because you're able to kind of increase that surface area of contact with the road in a sense. Anyway, so this is a starting point, but this seems reasonable. And during this assess step of our problem solving strategy, that would lead us to think that this is a reasonable answer. Now we've done the turning on a corner example, let's do a banked curve example. Banked curve is a common next example. Typical highway curves are banked 10 degrees or so. Maybe a little bit less, actually. But let's see how we design a banked curve. Okay, so we've got our incline, right? And the car is going on this incline, and it's graded at some angle theta. But of course, we're not on a flat surface, we're on an incline. So let's see our car, right? Don't break your neck trying to draw a car. Okay. Moving straight. I mean, its direction of motion is constantly changing, right? So anyway, so it went from 3D view to 2D view, but okay. So yeah, the direction's constantly changing. We're on this curve. What's this free body diagram look like? Again, let's consider the RZ plane. So what we're going to do is we're going to draw a picture that's going to look familiar, but we're not falling down this incline. That's the difference between this. That's the difference between this example and the ones from chapter 6, maybe even chapter 7, that we're not moving up and down the incline. The difficulty is that we're accelerating to the left. We're not accelerating up or down the incline. And so that's going to affect the free body diagram. We'll have again, for our axis, our z-axis. Now we have mg down. Okay. But the interesting question we're left with is about the normal force. If normal force points up and to the left because it's perpendicular, then the z component has to equal mg. So you have one of the components of the normal force equaling gravity, and the other part of the normal force, which we would call n sub r, that has to equal F net. And so these choices here of if the normal force is greater than, equal, less than, or depends on the mass, the correct answer is A. That the normal force has to be bigger than gravity for it to be in circular motion. And this is certainly different from those examples that we did in chapter 6 and 7, where you have the box sliding down the incline. If the acceleration is like that, if it's down or even if it's up the incline, if it's up or down the incline, well, it's always going to be accelerating down. Then you got mg down, and so the z or the perpendicular component of gravity would cancel the normal force, leaving the other component of gravity to provide the acceleration when we're sliding down the incline. So in the case of moving up or down an incline, the normal force is less than mg. But in the case of on a banked curve moving in a circular horizontal circle, the normal force is bigger than mg. So that's a really subtle point that folks often miss when we're talking about banked curves. And in fact, if the banking curve, we can even make it quantitative. If this is theta, the banking curve, usually with respect to horizontal, then that's the same angle that n makes with the z-axis. And so in looking at the sums of these forces, we're going to have, writing below here, I guess, in the z direction, we'll have n cosine theta minus mg equals 0. And so n would equal mg divided by cosine theta. Right? And a simple thought about cosine theta is that it's always less than 1. And so n, that's like a mathematical proof of how n has to be bigger than mg. Furthermore, in the r direction, we've got, I'll write it above it, in the r direction, we have n sine of theta equals f net, which for our purposes might be mv squared over r. And so when you set these two equal to each other, well, not set them equal to each other, if you plug in n, which is mg over cosine theta, you get mg tangent theta. And so the result is that v equals square root of rg times tangent theta. I skipped some steps, some algebra there. But this square root gives us the expression for velocity, well, I guess speed, around a circular tract without any friction at all. And so modern highways are designed with this in mind. It's designed like, say you want to have a speed set to 70 miles an hour. Well, that's about 31 meters per second. If you only have, 500 meters or so of radius to consider, like a little more of like a quarter mile turn, which is typical, then you'll have to adjust your banking angle to be that. Plugging in some numbers real quickly, you see that a banking angle of about 11 degrees on a radius of curvature of about 500 meters on Earth gives you a velocity of about 30 meters per second. So this is just an estimate of these sorts of, just an estimate of these sorts of angles. So banking angle of 11 degrees, which is not too unheard of. Radius of 500 meters, that's more or less expected for highway speeds. Maybe they might even be a little bit bigger, because if you make the radius bigger, you can make the angle smaller, right? And that might make it even less of an impact. And people might not feel people won't feel, because what are people going to feel? People will feel the normal force. And if you take it too quickly, obviously you feel like you're shoved down into your seat, right? I mean, this is one example, but if you're like taking a roller coaster and it goes real quick and then makes a quick turn, you're gonna, when it makes that quick turn, you're feeling shoved into your seat. That's because the normal force is pushing you along that direction. Now, what if you take it at a speed differently? So let's say we have these two values for theta and r. That means we can take this curve without the assistance or by itself. And in fact, if you think about like a cone, it turns out that, let's say that's a specific circle part of the cone. If the cone has some angle theta, the further, if you take it more slowly, so if you were switching from banked curves to this sort of theoretical moving in a cone problem, and this is a cone, not like a penny spinning thing that they have at the museums, which I'll get to in a minute. If you take this cone at anything slower than this prescribed speed, what will happen is you'll lower in radius and you'll be moving more slowly. And the idea is that the slower you get, the smaller your radius is. If you take it too quickly, if you take it faster than the prescribed thing, you'll start to spiral outward and be at a larger radius. So what happens now to the car if you take the curve at bigger or at faster than the prescribed rate? Let's look at the free body diagram, and then in one of your homework problems, you'll go through the mathematics of it. So if you're taking, so again, you're given r, you're given a radius of curvature and given theta, okay? And if they take the speed, if they take the velocity at bigger than square root of rg tangent theta, the only way to maintain that specific circular radius is now that friction has to come in. And this is where friction comes in banked curves. Same RZ axis. MG still points down. normal force still points up and to the left. It's still perpendicular, but now we have a static friction force that points down the incline. These two angles are both theta. So static friction points down the incline. Normal force points up, like that, right? And they work together to produce a larger F net. Because you have to have a larger F net to have a larger velocity in that specific radius. And so working out these equations is a little bit tricky. And for these small angles, there is a maximum to how fast you can take the curve. Because this, as of static friction increases, it'll get to the point where it's increasing so quickly that, or the static friction is so large that any other speed greater than the maximum speed will actually cause it to slip upward. It'll start to drift upward. And so setting up those equations takes a little bit of practice. And I think that's something that I want to leave for you guys, for you folks to practice on your own. Similarly, if you take it more slowly, how does the free body diagram change? Just draw that. So if you take this curve at less than square root RG tangent theta, now the friction actually switches direction. And so you have a friction, with mg down, now you have friction force up the incline. And now a smaller normal force with those same angles. And so now the static friction force has to kind of take away some of the normal force to make a smaller F net. So those are two separate examples. You might think, well, is there a limit to how slow you can take it? Not really. On highway curves, there's really no lower limit of speed, because you can see you can see cars parked on the edge side of the highway bank curve just fine. It's actually a little bit more subtle. And if people are interested, it turns out that in chapter 6, there's sometimes a problem where, like, you calculate a specific angle at which something starts to slip, and you can show that the coefficient, you can measure the coefficient of static friction to be the tangent of the angle at which it starts to slip. So that's the measurement of coefficient of static friction. So this angle is a thing that's important. For rubber on, rubber on concrete, mu sub s equals 1, which would make that angle 45 degrees. So it's really analysis. So if you're on an incline that is less than 45 degrees, then there is no minimum speed that you need to take it, but there is a maximum speed with which you can take it. And you're going to slip and drift upward. And if you turn that problem around, if you're on an incline, and this is what gets weird and almost like amusement park, or like, think motorcycles in a circle thing. If you're on an incline that is bigger than 45 degrees, again, the 45 is only there because we're talking about roads. That angle will be different for different surfaces. In that case, you actually have a minimum speed. Okay, there is a minimum speed with which you have to be moving a circle, otherwise you'll slide down, but there's actually no maximum speed with which you can take it. So, and what happens at 45 degrees, kind of hard to say. It's where you have two limiting cases, and in fact, this model might even kind of break down near an angle of 45 degrees. Because at 45 degrees is when it would start to slip no matter what. So you have to consider that as well. So it's a really interesting example. In your homework, there's a problem that makes this a little bit more theoretical, or it makes it a little bit more quantitative. So that is the banked curve example. So many examples of banked curves, but yeah, the normal force is always bigger than mg if it's taking it without friction. With friction, it'll be different. If you're taking it too fast, it's going to be much bigger than mg. It's possible that you take it so slow that normal force is even less than mg, but not at that specific rating. Okay, so that is banked curves.